Number 16. The friendly lie. A few meters down on a shallow reef in the western Pacific, the ocean still looks easy to read. The water is clear. Coral heads crowd the bottom. In the middle of all that color sits a flower-shaped animal armed with thousands of stinging cells. A small orange fish approaches, hesitates, and taps the tentacles with its flank as if testing a live wire. This should be the friendly part of the sea. The fish is small, bright, social, and famous enough to become a children's character. Its real life is harsher. A clownfish survives by nesting inside a venomous host that should reject it. Its safety depends on a chemical truce written into mucus. Its family hierarchy looks stable until it breaks. Remove the dominant female, and the breeding male can change sex and become her replacement. The familiar reef animal is real. So is the system underneath it. Survival here means negotiating with poison, and even body identity is conditional. That is where this descent starts. If one of the most recognizable fish in the ocean already lives by rules like these, the deeper water will not get simpler. Clownfish such as Amphiprion ocellaris and Amphiprion percula live in shallow waters of the Indian Ocean, the Red Sea, and the Western Pacific, often just 1 to 15 meters down. This is bright water, busy water, water full of things you can still name as fish and coral and shelter. That matters because visibility works against a small reef fish. In clear, sunlit shallows, predators can spot movement from farther away. There is less darkness to disappear into, fewer mistakes hidden by murk. A fixed refuge becomes valuable because being seen is almost constant. The refuge is an ambush animal. Sea anemones can look rooted and decorative from a distance. Up close, their tentacles are loaded with nematocysts, microscopic stinging harpoons that fire into passing flesh. For many small reef animals, touching those arms is a mistake measured in seconds. That is exactly where the clownfish lives. There are at least 30 species of clownfish, and they do not all use every anemone they encounter. Host range is limited. Some species associate with only a few anemone species, sometimes just one preferred set of hosts on a given reef. That specificity has a cost. If the right anemone is missing, damaged, or already occupied, the fish cannot simply settle anywhere bright and tentacled. The wrong host may sting too aggressively. Open water between hosts is brief on a map and deadly at fish scale. The partnership starts with contact, but not careless contact. Before a clownfish settles into its host, it performs a careful acclimation dance. It brushes and retreats, touches and backs off. The fish seems to build tolerance step by step until it can move through the anemone's arms without triggering the full response. Smithsonian points to a protective mucus coating as the leading explanation. That mucus appears to prevent the anemone from firing its stinging cells against the fish. Even here, in one of the most famous reef relationships on Earth, the mechanism is not completely settled. Scientists broadly agree the mucus matters. Exactly how the fish acquires or maintains that protection remains unresolved. And that uncertainty matters because the protection is not abstract. A juvenile searching for its first host may die before the bargain is complete. A fish displaced by a predator, a rival, or storm damage has to cross exposed reef and negotiate again. Miss the chemistry, lose the coating, or enter the wrong anemone too quickly, and the shelter stops being shelter. The tentacles fire. In shallow water, there is nowhere to hide while that mistake is happening. The clownfish is not only hiding in the anemone, it works there. A host anemone gets more than a tenant. The fish drives off intruders that nip at tentacles. It cleans away parasites and debris. Studies highlighted by National Geographic on February 27, 2013, indicate it may even help the anemone breathe at night. When darkness falls and photosynthesis stops, the fish's movement and ammonia-rich waste can improve water flow and deliver nutrients. Predators read this arrangement too. Many reef hunters avoid pushing directly into an anemone's stinging field, which is exactly why the fish stays close. Leave that radius and the protection drops sharply. A clownfish feeding a short distance from the tentacles is no longer buffered by venom it can tolerate better than its enemies can. The cost of leaving home is immediate exposure. Even this familiar scene has borders. Clownfish do not live in the Atlantic, the Caribbean, or the Mediterranean. Their world is narrower than the pop culture version suggests. Warm reef systems, host anemones, tight social groups. Geography matters because this survival system depends on the host existing at all. No host anemones, no chemical refuge, no defensive curtain to retreat into. Inside that refuge, rank matters too. The group is usually organized around a dominant female, a breeding male, and smaller non-breeders. If the dominant female disappears, the breeding male can become female and move up. That flexibility keeps the group going, but it also means stability depends on continuous replacement. When one body vanishes, every fish below it is forced to shift position in a hierarchy tied to a single, dangerous home. At the upper edge of the ocean, life still gives us animals we think we know. Bright colors, faces, families, homes. Look closer, and the familiar scene holds together only while chemistry, host identity, geography, and rank all stay aligned. In clear, shallow water, a clownfish survives by wearing the right chemical disguise inside the right animal at the right moment. If that system changes, even briefly, the reef does not turn dark or deep. It turns visible. Number 15. The glass cherub. In the cold upper ocean, a creature the size of a fingernail can look like a drifting ghost. Transparent body, orange-red core, two tiny wing-like lobes beating through the water. No shell, no hard armor, no obvious weapon. Yet the sea angel is a predator. You are looking at Cleone limacina, a shellless pelagic pteropod that moves from the surface to more than 500 meters down. Its body nearly disappears in the upper and midwater ocean, which makes the scene deceptive. It hangs in the cold blue water column as if it were carried there by accident. It is not. It is waiting. The name is the strange part. Sea angel sounds gentle, harmless. But this animal survives by hunting another drifter, the shelled pteropod known as the sea butterfly. One transparent animal with wings, one tiny shell with wings. Cute names, opposite roles. At first glance, the sea angel seems to do nothing at all. It hovers with those wing-like lobes and lets the current carry it. That is the illusion. Those wings are the relaxed posture of something built to strike from almost no distance. In water with no sunlight below, no shelter on the seafloor, and no room for brute force, even stillness can be a hunting style. Laboratory high-speed video catches the change in fractions of a second. A sea butterfly drifts within reach. Cleone opens its mouth in about 10 to 20 milliseconds. Then it inflates 6 buccal cones in roughly 50 to 70 milliseconds. The cones seize the prey's shell, rotate it, and bring the opening straight over the predator's mouth. The shell is not broken open by chance. It is positioned, held, turned. Then the animal inside is scraped out. At that instant, the angel stops looking like a ghost and starts looking like a machine. Small, precise, patient. A hunter that does not need speed in open water because its whole body is tuned for the only move that matters. That tuning is specific. The sea angel is not just chasing soft tissue in open water. It is intercepting a shelled prey item and using that shell as the point of control. The buccal cones do not grab an abstract victim. They grip a hard spiral, stabilize it against drift, and align the opening with the mouth. The strike depends on shape, rigidity, and timing. The sea angel is not a bottom creature. It is a pelagic hunter, suspended through the upper and midwater ocean, where food is scattered and bodies have to stay light enough to remain in the water column. Its feeding life is tied closely to the fate of shelled pteropods. If those prey thin out, the predator cannot simply switch off the loss and feed the same way on anything nearby. That is where the hunt connects to chemistry. The sea butterfly is more than prey. Scientists use shelled pteropods as indicator species for ocean acidification because their aragonite shells are vulnerable when seawater chemistry shifts and carbonate becomes less available. As the ocean absorbs atmospheric carbon dioxide, pH falls, and the conditions those shells rely on begin to change. The shell does not need to disappear overnight for the hunt to be altered. It only needs to weaken, pit, or thin. For the sea angel, that is not an abstract environmental note. A shell with surface damage may give the buccal cones a different grip. A thinner shell may flex or chip as it is seized and rotated. The item that is easier to damage is not necessarily easier to handle. If the shell deforms at the wrong moment, the opening may not align as cleanly over the mouth. The predator may have to re-grip, spend more time handling a single capture, or lose the prey in the water column altogether. And if weakened shells are a sign that shelled pteropods themselves are under stress, the problem widens. The immediate risk is not only a harder capture sequence, it is fewer suitable prey to encounter, more energy spent per successful strike, and less return in a habitat where food is already scattered. The sea angel does not need its own body to dissolve for changing chemistry to matter. Its dependence runs through the shell of something else. NOAA. Researchers have linked human-caused carbon dioxide to shell dissolution in pteropods along the U.S. West Coast. That does not prove a simple one-step outcome for every sea angel population. But it does mark a documented pressure on the prey this predator is built around. When the prey's shell changes, the predator's hunting conditions change with it, and that can plausibly affect feeding success, energy balance, and local abundance. So the threat is not only that a delicate shell may vanish, it is that a precision predator may keep making the same perfect move in water where the target no longer behaves the same way. The cones flare, the shell is seized, it starts to turn. And in a changing ocean, the tiny grip this hunter depends on may fail at the exact moment it was built to hold. Number 14. The floating trap. On a windy morning on Florida's Atlantic coast, the first sign is usually not the creature itself, but the flags. Then the color appears, a blue-violet bladder glinting in the wash like a child's balloon half buried in sand. Then comes the mistake. Someone sees what looks like a stranded jellyfish, steps closer, and learns that the sting is still active. NOAA warns that even after washing ashore, its tentacles can keep stinging for weeks. So what is the animal here? The float on the beach? The threads in the foam? Or the thing those pieces used to belong to? The myth is simple because the surface likes simple shapes. A Portuguese man-o-war looks like one creature, one float, one drift, one sting. It even has a proper species name, Physalia physalis, as if that settles the matter. But the evidence does not cooperate. It is not a jellyfish. NOAA classifies it as a siphonophore. Siphonophores are colonies, genetically identical living units fused into a single working system. Not one body with many parts, but many bodies reduced until each can do only one job. This is the first stop on the way down where life answers the larger question with a cheat. If the ocean begins with animals we think we recognize, this one abandons the ordinary idea of an animal almost immediately. At the surface, it is already built like something from the deep sea. Start with the part most people notice. The float rises about 6 inches above the waterline, blue, violet, sometimes pink. It is a gas-filled sail just tall enough for the wind to grab. Below it hangs the other half of the trap. Tentacles trail into the sunlit layer, where small fish and plankton move through open water. In large Pacific relatives commonly called bluebottles, those tentacles can extend to around 10 meters. You do not need abyssal darkness for a body plan to become strange. You only need current, wind, and prey that swims into invisible thread. That thread breaks the second myth too. People talk about the sting as if the animal chooses to attack. It does not. The discharge is reflex. The stinging cells fire when triggered, whether the tentacle is attached, torn free, or stranded in surf. On the beach, it feels malicious because the mechanism stays armed after the colony has come apart. Officially, this is a drifting colonial cnidarian. In practice, a severed piece can keep doing its one job with no brain making a choice. There is a reason it feels engineered. Most famous siphonophores show up much deeper down, in ROV footage, as transparent chains and curtains haunting black water. But NOAA describes the Portuguese man-o-war as the only siphonophore species living in surface waters. The evidence points in two directions at once. It belongs to the very top of the ocean, where sunlight is strongest and waves are visible from shore. Its design belongs to a group better known for turning the midwater and deep sea into drifting machinery. You are looking at a beach hazard. You are also looking at a colonial blueprint the ocean keeps reusing in stranger places below. The usual labels never quite fit. Jellyfish is visually convenient, but structurally wrong. Floating animal is closer, but still incomplete. In every ocean except the Arctic, and often washing up along Florida coasts after onshore winds, the man-o-war does not really swim where it wants. It sails. The float catches air. The colony drifts. The tentacles fish beneath it. Surface weather becomes locomotion. Chance encounters become feeding events. The trap is not chasing anything. It is being towed across the skin of the sea. So go back to the question from the sand. What part of it is the actual animal? Not the float alone, not the tentacles alone, not some hidden central body waiting to be identified as the real one. The official picture calls the Portuguese man-o-war a single species. But on the water, the thing doing the living is a colony of specialized zooids. One set forms the gas-filled float. Others handle feeding and defense with stinging tentacles. Others are devoted to reproduction. What looks like one organism with parts is, in the stricter biological sense, a cooperative stack of reduced living units. Each is built for one task and unable to do the others. The balloon is alive. The fishing lines are alive. The reproductive structures are alive. The animal people think they saw on the beach is, officially, one siphonophore. In practice, it is a fleet. Number 13. The disappearing lantern. From around April to May, firefly squid gather in Toyama Bay to spawn. Seasonal notices put it that way: calm, tidy, almost bureaucratic. Spring nights on Japan's central coast look nothing like that. Nets rise. The catch is disturbed. Blue flashes break across the water. The glow is brief and precise enough that Toyama Prefecture sets aside roughly 15 kilometers of protected coastal habitat for it. Fishermen know the timing. Tourists wait for it. The animal making that light is tiny. A squid barely 7 centimeters long if female, about 6 if male. It looks like something that should stay hidden. Most of the year, Watasinia scintillans is nowhere near the shoreline. It lives far offshore, in a vertical band where glowing is common enough to be almost normal. Roughly 200 to 1,000 meters down in NOAA's broader deep-sea bioluminescence work. That depth matters. Past about 200 meters, one of the ocean's oldest rules stops working. Photosynthesis is over. Sun-built color is no longer the main language. Visibility does not vanish, it gets meaner. Down here, light is still present, but only as a dim, cold wash leaking from above. Blue travels farthest. Shapes outlast color. The question is no longer what hue you are or what pattern you wear. It is simpler than that. Can anything below see your outline? That is the hard turn between the familiar surface world and the stripped-down logic below it. In this layer, being seen can be worse than being touched. The firefly squid handles that with hardware. Along its body and arms are photophores, light organs that produce blue light. One study puts it around 470 nanometers, right in the part of the spectrum seawater carries best. At the tip of each of its 2 ventral arms sit 3 especially intense, luminous organs. These are not scattered sparkles. They are placed points of light, exactly where another animal would notice them. That sounds like a bad survival strategy. Sometimes it may be. Sometimes it may be the point. The literature does not settle on a single use because the evidence points several ways at once. The light may draw prey closer. It may confuse predators. It may help squids recognize their own kind during the spring spawning migration. One visual study goes further. The eye itself appears adapted to distinguish the species' own bioluminescent signal under dim, downwelling light. The animal does not just carry lamps. It may be built to read them. The glow is not decoration. It is part of how the squid operates. That is what makes the shoreline display in Toyama Bay matter beyond tourism footage. What people see there is not an isolated trick. It is a surface glimpse of a deep-sea solution. Many ocean animals bring light into darkness, but the firefly squid shows the logic cleanly. In a world with faint blue above and near black in front of you, light can be lure, signal, warning, and camouflage at the same time. There is still the beachside problem. Why would an animal this small, this edible, this exposed, light itself up so boldly? Because the same body can do 2 opposite things depending on the angle. Seen from the side, a flashing squid is a message. Seen from below, it becomes a silhouette. That is what hunters track in dim water under the last surviving sunlight. A dark shape crossing a pale ceiling is enough. No color needed. No detail needed. Just contrast. The squid answers contrast with counterlight. NOAA's general bioluminescence material describes the principle across the deep ocean. Animals use belly lights to match the downwelling light above them. That reduces the shadow of their bodies when predators look up. The firefly squid is one of the clearest cases. The glow underneath is not there to make the squid stand out. It is there to remove the one outline that matters. From shore, the spring spectacle looks like advertisement. A blue animal scattering sparks through black water, almost signing its own location. Offshore, past that 200-meter threshold, the same light does different work. Sunlight no longer feeds anything there, but it still exposes everything. Color loses authority. Shape takes over. Survival depends on managing the little light left. By the time the firefly squid reaches nets and human eyes, you are looking at a body tuned for that harsher geometry. The arm tips flare, the body glows. The bay answers with blue. Underneath, where a hunter would be scanning for a clean black cutout against the surface, the squid does something quieter. It fills in its own shadow. The outline softens, thins, and nearly disappears into the last light falling from above. Number 12. The visible organs. At 700 meters off Alaska, NOAA's camera catches a squid that almost disappears before you understand what you are seeing. The body is there, but only barely. A long, pale vessel hangs in black water, so transparent that your eye lands first on what sits inside it. A dark red digestive gland, white gills, small points of light organs. The animal has stripped away the wall and left the machinery floating. Start with the body. This is not thick muscle built for a fast hunter near the surface. Not armor, not a heavy shell. Glass squids, the family Cranchiidae, are built for midwater, where survival often means not being seen in the first place. Their bodies can be transparent or translucent, but the trick is incomplete. A squid still needs a gut. It still needs gills. It still needs eyes, and those dense parts make a visible knot inside the blur. Depth makes that problem stranger. Juvenile cranchiids can drift higher in the sunlit zone, where ordinary squid are outlined by sharp beams and shadow. As they grow, many descend into darker midwater and even bathypelagic layers. The same animal has to work in two worlds, one that exposes shape and one that magnifies whatever contrast remains. In the deep, being easy to see can mean being easy to eat. The footage makes that cost obvious. NOAA's view of Taunius borealis at roughly 700 meters, about 2,300 feet, does not show a smooth ghost. It shows compartments. The digestive gland glows red, the gills sit pale against the black water, and the photophores appear as separate points rather than a blur of light. Another NOAA record, a cranchiid nicknamed the piglet squid, shows the same thing at nearly the same depth. The outer body fades, but the interior stays legible. Here is the body that vanished before its organs could. The glass squid. That creates a camouflage problem you can almost diagram. A predator below, looking up into the last diluted light, loses the broad dark mass if the mantle is transparent. But the eyes are still dense, rounded, and optically awkward. The digestive gland is still pigmented. The gills still leave a pale trace. Transparency removes one target and leaves a cluster of others. In midwater, that cluster can be enough to trigger a strike. This is the same zone where many animals live as moving shadows, and where a mistaken outline can be fatal. A squid that stands out for even a second may give away its position to a fish, or a larger squid hunting from below. The cost of being visible is not abstract here. One bright silhouette can end the meal, the migration, or the animal itself. Glass squids belong to a community that solves visibility by subtraction. Less edge, less bulk, less dark tissue offered to the water around them. Their silhouette depends less on hard structure than on buoyancy and soft internal arrangement. They do not answer pressure and darkness by becoming compact tanks. They become easier to overlook. Even the family name only captures part of it. Glass sounds ornamental. But the footage shows a practical design under pressure. If the outer body goes pale enough, the animal stops reading as one solid shape and starts reading as a few separate marks drifting in black. Organs remain, and the eyes remain hardest to hide, because no amount of transparency can erase the geometry they need. The first glimpse hides that struggle. At 700 meters, the squid looks as if it solved visibility by deleting itself. It did not. The problem just moved inward, to the organs transparency cannot hide, and the next movement in the dark may already be searching for them. Number 11. The red stomach. The stomach designed to hide a murder. What if the brightest clue on an animal exists because light itself has failed? In 2001, when Stephen Harbison, Shinsuke Matsumoto, and Bruce Robison formally described a deep-sea comb jelly from Pacific midwater, they gave it a name that sounds almost too dramatic for its job. Lampoctus cruentiventer. Brilliant comb. Bloody belly. The contradiction shows up at once. Why would a deep-sea animal be bright red in a place where color should be useless? Off Monterey Bay, that question started in front of ROV cameras, not with a preserved specimen in a jar. Something soft and lobed drifted through the black water, almost theatrical in the lights. Its comb rows shimmered, thin, iridescent bands sliding like moving chrome. Inside that delicate body sat a deep red stomach, dark as spilled ink. Monterey Bay Aquarium later pointed to that split as the whole point of the animal. The genus name, Lampoctius, comes from Greek roots meaning brilliant comb, a nod to the flashing cilia. The species name, cruentiventer, points to the blood-colored gut. One animal carries both signals, and at first they seem to clash. You are about 986 meters down, in the range where one recent observation placed it at Southern Hydrate Ridge. Sunlight is gone. The water is cold, black, and under pressure that would crush an unprotected surface animal without ceremony. A jelly drifting here should follow one obvious rule: do not advertise yourself. Yet this one seems to break that rule from the inside out. The comb rows catch and scatter light. The stomach looks painted red. For a moment, it reads like bad camouflage, a design better suited to shallow reefs and warning colors than to midwater, where outline is everything and one visible organ can betray the whole body. But seawater strips color fast. Red wavelengths are absorbed quickly. They do not travel far. Tissue that looks vivid in an aquarium or under white lights does something else entirely in the deep. It stops being red in any useful sense. It disappears. At depth, red reads as black. The picture changes completely. The bloody belly comb jelly is not carrying a warning flag. It is carrying a blackout curtain. Comb jellies eat glowing things. Not always, not exclusively, and not in ways we have fully mapped for this species. But deep midwater is full of animals that answer danger with light. Swallow the wrong prey, and the meal keeps shining inside you. A transparent predator turns into a floating confession. In a zone where so many bodies work to erase edge, erase contrast, erase the fact that they are present at all, a luminous gut would be a disaster. The red stomach may exist for the same reason a submarine runs dark. It hides what the animal has already taken. The footage makes that idea feel less like poetry and more like engineering. The outer body is gelatinous and delicate, a structure that seems barely assembled. But deep sea life keeps arriving at the same answer through different materials. If you cannot outrun every threat and you cannot armor every surface, then you hide the evidence that you are feeding. The bloody belly comb jelly does it with pigment placed exactly where the problem would flare. Not across the whole body, in the stomach. BARI scientists first described the animal about 20 years ago, and even that timeline says something about the deep sea. Some creatures are not only hard to spot, they are hard to keep, hard to culture, hard to bring up without destroying the very body plan that works so well below. Monterey Bay Aquarium later became the first aquarium anywhere to exhibit bloody belly comb jellies. That was a display milestone, but it was also a reminder of how recently this animal moved from remote footage into live observation. We have a formal description, we have a name, we have taxonomic placement, order Lobata, family Lampoctenidae. A named species is still not a fully known one. That uncertainty fits the larger pattern in this descent. As sunlight disappears and ordinary body structure falls away, life does not get simpler. It gets stricter about what remains visible. The glass squid used subtraction. The bloody belly comb jelly solves the same problem another way. It leaves the body pale and active. It lets the comb rows shimmer when light hits them. But it darkens the one chamber most likely to betray a kill. So the color that looks most dramatic under a camera may be the one least visible in the animal's real world. The red is for us. Down there, it is nearly black. When a swallowed bioluminescent prey item flashes inside the gut, the light does not spread through a clear, drifting body. It dies in a dark red stomach, and the animal keeps drifting. Number 10. The false seafloor. The fathometer recorded a bottom at 300 fathoms, the report said. A little later, the bottom rose. Before dawn, it fell again. There was no storm. No reef on the chart. The seafloor seemed to climb toward the ship in the night, then sink away by morning. 20th century sonar operators kept meeting that same puzzle in open water. An echo appeared deep below the hull, solid enough to read like ground. But it did one impossible thing. It moved on a schedule. A mass of animals was imitating the bottom, and the mistake mattered. If sound could confuse living biomass for terrain, then the midwater ocean was not empty space between surface and seabed. It was structured, crowded, and active enough to distort how humans mapped, hunted, and measured the sea. By day, much of that biomass holds in the mesopelagic, roughly 200 to 1,000 meters down, where the last usable sunlight fades into near-black water. At dusk, the screen changes because the animals begin to climb. Not a few strays. Across the world ocean, billions to trillions of animals rise each night to feed near the surface, then descend again by day to hide. That daily movement is often called the largest animal migration on Earth. But the scale is not just impressive. It means predators can time their hunts to it, fisheries can mistake or target it, and vast amounts of carbon can be moved downward one night at a time. Lanternfish are one of the main reasons this migrating layer looked like a false bottom. Fishbase lists the family Myctophidae at 34 genera and about 250 species, marine and circumglobal. The number matters because it helps explain reach. This is not one local swarm creating a quirky sonar artifact. It is a globally distributed family, diversified across oceans, helping build a layer so persistent and widespread that generations of instruments kept finding it. Lanternfish are among the most abundant vertebrates in the ocean. When echo sounders picked up a seafloor rising after sunset, they were detecting animal density on a scale large enough to affect navigation, biomass estimates, and our picture of where ocean life actually sits. Picture the timing. Sunset above, black water below. Then countless small bodies begin moving up from hundreds of meters down. They climb because the upper ocean holds more food. It also holds more eyes. The migration runs along that edge, between hunger and being eaten. Feeding matters. Predator avoidance matters. Energy conservation matters. Different species likely weigh those pressures differently. That is the complication hidden inside the clean sonar line. What looks from a ship like a single band is really a shifting compromise among prey, hunters, light, and risk. Lanternfish are built for that commute. Their bodies carry photophores, light-producing organs arranged in species-specific patterns along the belly and flanks. In shallow water, glowing would seem absurd. In the twilight zone, it can hide you. A fish seen from below is outlined against the faint light leaking down from the surface. A controlled glow underneath can erase that silhouette. The fish does not shine to be noticed. It shines to cancel itself. Smithsonian's ocean material describes one lanternfish with a nasal light organ, a tiny headlight where a nose would be. Not for spectacle. Survival in water, where seeing and vanishing are part of the same task. Lanternfish are not only surviving in that darkness, they help move the ocean's economy. Noé's deep pelagic material describes mesopelagic fishes as a link between surface production and the deep sea. In practice, that means bodies moving carbon. Lanternfish rise toward food produced in the lit upper layers, feed there under cover of darkness, then carry that captured carbon back down when they descend. They are also eaten in huge numbers by larger fishes, squid, seabirds, and marine mammals. A fish only a few centimeters long becomes part of a planetary conveyor, transferring energy upward to hunters and carbon downward into deeper water. If that biomass is larger than we thought, then so is its role in climate-linked carbon flow. If sonar misreads it, then some of that accounting is still uncertain. That is why the false bottom effect is more than a sonar curiosity. It revealed an ocean process that is easy to overlook, precisely because it happens in darkness and in motion. A layer dense enough to mimic ground can also hide prey from one instrument, expose them to another, and redraw the nightly map for anything that feeds by sound, sight, or timing. For predators, this migration is not scenery. It is a moving meal that rises on schedule. For scientists, it is a reminder that one of the planet's largest animal movements was first noticed as an error. The official term was the deep scattering layer. Accurate, dry, bureaucratic almost. But the screen told a stranger story. The seabed seemed to rise at night and meet the ship. It was not seabed, living biomass, globally spread, carrying carbon, feeding hunters, and still only partly resolved by the tools that found it, leaving open how much of the ocean's hidden traffic and hidden weight sound still fails to separate from the dark. Number 9. The transparent head. In 2004, an MBARI remotely operated vehicle drifted through Monterey Canyon at 744 meters and found a fish that looked wrong in a very specific way. It was only about 15 centimeters long. It hung motionless in the midwater. The front of its head seemed to be a clear dome. Inside that dome sat two green tubes aimed straight up. If those were really its eyes, then this animal had a problem. It could watch the water above it. It could catch the silhouette of a copepod or the flash of bioluminescence overhead. But anything directly in front of its mouth should have vanished from view the moment it tried to feed. That contradiction followed the species for decades, because almost nobody had seen it alive. In 1939, ichthyologist Wilbert McLeod Chapman described Macropinna microstoma from the North Pacific. For most of the 20th century, though, the barreleye was less an animal than a ruined specimen. Nets brought it up from roughly 600 to 800 meters. By the time it reached the surface, the strangest part had collapsed. The transparent shield over the head was too fragile. The body survived badly enough to classify. The mechanism did not. So the fish entered books as a deep-sea oddity with tubular eyes that appeared locked upward. A design so impractical it almost looked like a mistake. But the face was already lying. Those dark spots above the mouth, the features that instantly read as eyes, were not eyes at all. They were nares, sensory openings used for smell. The real eyes were deeper in the head, two green barrels tucked inside the fluid-filled dome. Seen from the front, the animal looked simple. Seen correctly, it looked engineered. The standard image of the barreleye hardened around that mistake. It became a fish condemned to stare at the ceiling. Useful, maybe, for spotting prey silhouetted against the faintest trace of downwelling light. Apparently useless for the last part of predation, when prey has to be lined up, approached, and swallowed. A hunter that can detect food but not track it into its own mouth is not a working design. It is a paradox. The fish that turned its skull into a window carried that paradox for nearly 70 years. Then the living animal stayed intact long enough to give itself away. MBRI's video showed the barreleye suspended like a tiny submarine with a clear cockpit. It did not rush. It did not lunge. It just held position in the dark water column. That mattered. Midwater predators often survive by reading what passes above them. But Bruce Robison and Kim Reisenbichler still had the same mechanical problem in front of them. Upward-looking eyes explain detection. They do not explain feeding. On February 23, 2009, MBARI published the detail that changed the whole animal. In a shipboard aquarium, a live specimen finally stayed intact under conditions that did not destroy its head. The tubular eyes moved. Not a twitch, not a slight adjustment. They rotated forward through an arc at about 75 degrees. The fish was not fixed in a permanent upward stare. It could scan the water over its head, then pivot its gaze toward what was directly ahead when it moved in to feed. That single motion rewrote every dead specimen that came before it. Now the dome made sense too. The transparent tissue was not just spectacle. It was field of view. A clear shield over the top of the head let the fish protect those sensitive tubular eyes while still looking upward through them. Protection may have mattered for more than pressure and fragility. MBARI linked the barreleye to a stranger feeding strategy, hovering among the tentacles of siphonophores and stealing prey from their grasp. In that setting, delicate forward-facing eyes would be a liability. A transparent shield over rotating eyes looks less like ornament and more like armor. Picture the geometry. A small fish in black water. Above it, drifting traps and loose zooplankton. First the eyes point up, watching for silhouettes and glows. Then prey is close. The green tubes swing forward inside the clear dome. The mouth lines up. The attack comes from below. Even that does not finish the case. Direct observations are still rare. Scientists know the barreleye likely takes zooplankton and small crustaceans. The siphonophore theft idea fits the anatomy disturbingly well. But how often it feeds that way in the wild is still unresolved. The fish remains half seen, which fits an animal misread by the part of it that looked most obvious. In the larger descent through the ocean, this is where the pattern starts to shift. Strip away the familiar face, and the familiar face can turn false. Strip away ordinary body structure, and a skull can become a viewing chamber. For 70 years, the apparent flaw looked simple. The eyes seemed trapped, aimed at the surface, unable to help with the kill. The correction was simpler and stranger. The eyes on the face were its nostrils. The true eyes sat inside a transparent head and rotated forward. Number 8. The private searchlight. The predator with a color only it can use. Why would any hunter in the deep ocean bother making red light when red is the first color seawater erases? At 100 to 1,000 meters down in the Pacific midwater, sunlight is already failing. Food is thinly spaced through a black column. Red should be wasted effort. It should vanish almost at once. But one fish built part of its life around exactly that impossible choice. In 1890, the ichthyologist Charles Henry Gilbert described a species he named Idiacanthus antrostomus. Today, the Monterey Bay Aquarium lists it as the Pacific black dragon. Not on exhibit, hardly a surprise. This is a deep-sea midwater predator from a layer where animals are more often recovered than introduced, and where being seen can mean being eaten. At the surface, in photographs, it looks almost theatrical. A long black body, needle teeth, a face designed by someone who had lost patience with moderation. But the animal itself belongs lower down, beneath ordinary blue, where a body has to justify every gram and every glow. Stay with the female for a second because she is the hunter. She can reach about 24 inches, 61 centimeters. For a dragonfish, that is substantial. Her mouth is lined with fang-like teeth. A barbel hangs from her chin like a loose wire, a lure in black water. She takes crustaceans, shrimp, fishes, whatever can be intercepted and swallowed before the dark closes again. That already makes her an efficient midwater ambush predator. It still does not explain the red light. It makes the puzzle sharper because light is expensive, and deep-sea animals do not spend energy on decoration. Look past the teeth and the barbel. Look at what she can see. Most bioluminescence in the ocean is blue or blue-green for a blunt reason. Those wavelengths travel best through seawater. Blue carries. Blue advertises, disguises, startles, warns. Red does the opposite. Red is stripped out so quickly near the surface that by the time you are down in black dragon territory, there is effectively no ambient red light left at all. That should make red useless. Instead, it makes red private. If almost nobody down there can detect it, a red beam is not a beacon. It is a channel shared by almost no one else. The fish starts to feel less like a monster and more like a tool built for one narrow job. Some dragonfish in the stomide group are known to produce red or far-red bioluminescence. Some carry visual pigments specialized enough to detect those wavelengths when many prey animals cannot. The black dragon sits inside that lineage. Picture the trick in practical terms. The water is black. Prey is sparse. A shrimp or small fish drifts ahead, invisible except at close range. The hunter switches on a color the neighborhood is effectively blind to. For the prey, nothing changes. For the predator, a target appears. It is the deep-sea version of a flashlight only one set of eyes can use. By this depth, life is no longer just reshaping the familiar fish body. It is dividing access. One set of animals lives inside the light available to everyone. Another makes its own light and restricts who can read it. The ocean began with creatures we recognize: fins, eyes, mouths, pursuit. Here the contest shifts from muscle to information. Advantage goes to the animal that can detect what the other does not even know exists. The species pushes that logic further than the face suggests. The male Pacific black dragon is so reduced he looks almost unrelated. About 3 inches long, 8 centimeters, brownish, toothless, and without a stomach. Not a small hunter. Not even a functioning feeder. An adult male cannot eat at all. His life is compressed into a single job: survive long enough to mate. The female is armed for pursuit in a food-poor dark. The male is built for urgency and little else. In shallow water, that split would seem absurd. Down here, it is accounting. If energy is scarce, anything not essential gets cut. One sex carries the lure and the specialized vision. The other is a brief delivery system. Same species. Two separate solutions to the same darkness. There is an uglier footnote. The aquarium notes that what enters the ocean can eventually reach the deep sea. Debris dropped into the bright world above does not stay there. It sinks into habitats like this one, into the path of an animal already living on strict margins. That is easy to miss because the black dragon looks alien enough to seem sealed off from us. It is not. Gravity keeps the connection open. Still, the strangest fact is the first one. The red light was never meant for the whole ocean. It was meant to leave most of the ocean out. A female Pacific black dragon moving below 400 meters at night carries her own narrow illumination through water where red has no background presence, and where many animals lack the pigments to register it. To them, she is hunting in darkness. A shrimp snaps into outline for a moment, the chin barbel hanging beneath the teeth. Then the light goes out. Number 7. The attached male. On November 17, 2014, the lights of MBARI's remotely operated vehicle Doc Ricketts cut through Monterey Canyon at about 580 meters, and a black shape drifted into view. It was barely 18 centimeters long, and that size matters. In the deep sea, a body this small can vanish between meals, or a little larger can survive only by waiting. In the camera beam, it looked enormous. A round head, a mouth already open, teeth like bent needles, and a glowing lure rising from the skull like a fishing rod made of bone and light. She did not charge. She hovered. In a part of the ocean where a missed meal can matter for weeks, even motion has a budget. The lure is the first thing everyone notices. The obvious question is how anything falls for it. The animal in front of the camera was a female black sea devil, Melanocetus johnsonii, one of the deep-sea anglerfishes most people know as a nightmare illustration, rather than a living fish. Usually they reach us dead, hauled up from depth with their tissues damaged and their posture collapsed. But here she was, alive in the bathypelagic dark, between 100 and 4,500 meters of known range, suspended exactly where sunlight has failed and food arrives by accident. In that world, the body stops being elegant and starts becoming efficient. A huge mouth means any passing fish or crustacean might count. Long teeth mean prey that enters does not leave. And the lure means darkness itself can be turned into bait. Nobody knows exactly what the fish in the ROV lights thought she was imitating. A worm, a larva, a tiny wounded animal. The sharper truth is that she may not need to imitate anything well. Black water, a small living light, is already enough to trigger curiosity, and curiosity can be fatal. You are a crustacean or a juvenile fish in open mid-water. There is no seafloor to hide under, no reef, no weed bed. Then a pinpoint glows ahead of you, faint and local in a void that is otherwise empty. You move closer because almost everything worth finding down here announces itself by being there at all. The mouth is already waiting. That is the quiet brutality of the black sea devil. It is not a fast predator. It is not a relentless chaser. It is a suspended trap with teeth attached. The 2014 female moved slowly in the water column, using minimal effort. And that matters because this is what life begins to look like when sunlight, speed, and abundant food have been stripped away. Every burst of motion burns a precious reserve. Every missed strike can mean days of hunger. Hunting turns into patience so complete it barely resembles pursuit. Mbari's team collected her after the sighting. At the surface, she survived only briefly. So the most famous live black sea devil ever filmed also came with a limit. We saw a living animal, but only for moments, and under artificial light in a world where almost no one gets to watch normal behavior for long. That uncertainty clings to the footage. Was she hunting as usual? Disturbed by the vehicle? Already stressed? We cannot say with confidence. But we can say what her shape was built to solve, because the deeper problem is larger than feeding. Finding prey in the midnight zone is hard. Finding a mate can be worse, and failing means no offspring at all. A female black sea devil may grow to about 18 centimeters. A male of the same species is listed at just 2.9 centimeters. Same fish, same darkness. Two body plans so unequal they barely look related. The female carries the lure, the mouth, the ambush apparatus. The male is reduced to a search mission in a world too large for him to control. In some deep-sea anglerfishes, that search ends in one of the most extreme reproductive strategies known among vertebrates. The male finds the female, bites her, and does not let go. Tissues fuse, circulatory systems join. He stops existing as an independent animal and becomes a permanent source of sperm. Black sea devils have been documented with attached males, although not every species of anglerfish handles attachment in exactly the same way, and not every case means total lifelong absorption. But the direction of the solution is unmistakable. Out here, the cost of missing your one chance is so high that courtship can collapse into merger. The open ocean is vast, dark, and thinly populated. If a male drifts past the only female he will ever encounter, there may be no second meeting. So evolution does the arithmetic no land animal would ever choose. It reduces one sex almost to a search organ, then turns success into dependency. At first, the lure looks like the whole story, a lamp for deceiving prey. But the black sea devil's real crisis is not just getting dinner. It is solving two absences at once. Food is rare, yes, but companionship is rarer, and both shortages punish the same weakness: being alone in a place that does not forgive delay. The female waits in darkness for something to approach. Sometimes that something is supposed to be eaten. Sometimes it is supposed to stay. Somewhere beyond the beam of the ROV, beyond the one animal we happen to see on one November dive in Monterey Canyon, there is a male no larger than a fingernail, moving through black water by scent and chance, trying to locate a body he cannot afford to miss. If he finds her too late, he dies alone. If he finds her early, he may lose himself entirely. And if he fails to find her at all, the next hunger in the canyon will belong to him. Number 6. The fake vampire. On a blackwater dive in Monterey Bay, the ROV lights catch something that looks like a bad idea made flesh. 2 red eyes, a body about 12 inches long, 8 arms joined by a cloak of dark webbing that opens like a little cape in the beam, and the name does the rest. Vampirotuthis infernalis. Carl Chun gave it that scientific label in 1903. Literally, the vampire squid from hell. The registry sounds final. The shape sounds predatory. The setting helps. This animal usually turns up 2,000 to 3,000 feet down, roughly 600 to 900 meters, in one of the least welcoming layers in the sea, the oxygen minimum zone. Water with so little oxygen that many fast hunters pay heavily just to remain there. If the ocean starts with creatures we can recognize, this looks like one more step away from us. Not just darker, meaner. But in the camera lights, it does almost nothing. It hangs there, neutrally buoyant, dark red shading to black, spending almost no energy at all. No charge, no pursuit, no burst of jetting after fish. That restraint is not laziness, it is the design. Researchers have measured in this animal one of the lowest mass-specific metabolic rates known for any cephalopod. In a layer where oxygen is scarce, wasting effort is expensive. So the vampire squid survives by refusing the whole pace of the chase. The scene flips there. Its hell is also its shelter. The same oxygen-poor water that sounds like punishment excludes many active predators that need more fuel, more ventilation, more speed. Faster animals are limited by the chemistry around them. This one settles into it. And then the name starts to slip. The monster that survives by eating snow does not hunt the way its cloak suggests. It waits for debris, marine snow, fecal pellets, bits of dead zooplankton, small crustacean remains, even the discarded mucus sinkers produced by larvaceans higher in the water column. Other animals feed, shed, excrete, die, and leak. Their leftovers drift down through the dim middle sea. The vampire squid lives on the fall. To collect it, it uses 2 long retractile filaments, not the feeding strike you expect from a squid in a horror title. The filaments extend into the water, gather the suspended particles, and bring them back toward the arms. The animal wipes that material along its arm surfaces, coats the mess in mucus, and eats it. No ambush, no blood, just a patient harvest of whatever the water is shedding that day. The taxonomy feels strange for a reason. It is not a true squid. It is not a true octopus. It belongs to its own lineage, Vampiromorpha, a leftover branch still living in the midwater dark. The body reads like a warning because evolution built it under deep-sea rules. The lifestyle is closer to a recycler than an executioner. That does not mean it is defenseless. It still knows how to perform. When threatened, the tips of the arms can flash with blue photophores. And unlike many shallower cephalopods, it does not rely on an ordinary ink cloud. In the deep, black midwater, dark ink is a weak bargain. So it releases something far stranger, a cloud of bioluminescent mucus, glowing in the water while the animal slips away. The effect is theatrical because it has to be. Down here, one hesitation can put you inside someone else's mouth. The record gives you a vampire from hell. The footage gives you a suspended drifter in oxygen-starved water. The body gives you a cloak, red eyes, and a set of tricks for vanishing in the dark. But the daily reality is much less dramatic and, in its own way, much weirder. This animal survives in a part of the ocean that pushes body plans toward extremes. Yet its answer is not force. It is economy. Spend almost nothing. Live where pursuit is too costly. Let the surface world feed you by accident. And that official name keeps overpromising violence it never delivers. Because on the monitor in Monterey Bay, inside a zone many predators avoid, the so-called vampire is not drinking from prey at all. It is extending filaments into falling debris, wrapping marine snow and larvation mucus in more mucus, and swallowing the trash. Number 5. The armored scavenger. A carcass does not stay a carcass for long at depth. Once a giant isopod finds it, the meal can become a trap. Too much food, too fast, in a place where the next chance may not come for years. The animal swells itself on a windfall it cannot predict, then carries that risk back into the dark. In the deep sea, survival is not only about enduring famine. It is about surviving what happens when famine briefly ends. In January 1879, in Paris, Alphonse Milne Edwards stood before the French Academy with an animal that looked wrong in scale. Not a crab, not a lobster. An isopod, a marine relative of the pillbug in your garden, hauled from 955 fathoms, about 1,747 meters down. The deep sea had only just stopped being treated as a lifeless void. Yet here was something plated like armor, with hooked legs and wide, dark, compound eyes, reaching up to 36.5 centimeters long, the largest known isopod on Earth. Its size feels impossible in a place with so little to eat. The bathyal seafloor is a pressured desert. No sunlight. Near freezing water. Food falls by accident from far above. In that starvation zone, this animal did not merely persist, it became huge. The encounter is unsettling because the body makes its purpose obvious. 7 overlapping dorsal plates cover the back like sections of a gauntlet. Behind them, a broad tail fan braces and steers on the bottom. 7 pairs of legs are built not for speed, but for marching over mud, wreckage, and meat. Under the head, the mouthparts tear whatever the surface loses. Dead fish, squid, chunks of flesh, anything that sinks. More than 20 species of giant isopod are now known in the genus Bathynomus. Bathynomus giganteus became the emblem because it surfaced at exactly the right scientific moment. In 1878, during U.S. Coast Survey dredging in the Gulf of Mexico and Caribbean under Alexander Agassiz, one of these armored animals came up in a catch meant for mud, shells, and fish. Instead, the crew found what looked like a deep-sea woodlouse the size of a dinner plate. That mattered. The abyss was no longer hypothetical emptiness. This animal did not look accidental. It looked established. A century later, cameras found the same answer still moving across the same depths. In 2021, NOAA's Okeanos Explorer recorded Bathynomus giganteus in the Gulf of Mexico at 984 meters, 3,228 feet. Pale, segmented, crossing the seabed with the slow certainty of a machine that has never needed to hurry. The instinct is to call it a monster bug. That misses the point. It is an undertaker built for interrupted abundance. Its most famous talent is almost absurd. Captive giant isopods have been documented surviving more than 5 years without food. Not every captive animal does it, and the exact trigger remains unresolved, but the capacity is real. The metabolism runs on a different clock. That fact alone, though, is too simple. Scarcity is only half the problem. A scavenger in the deep sea also faces dangerous concentration. When food arrives, it may arrive as a bonanza large enough to draw every scavenger in range. A carcass is not just nutrition. It is a brief, crowded event. Delay too long, and the meal is stripped. Feed recklessly, and the swollen body becomes slower, more vulnerable, harder to move. Giant isopod is built for shortage, but shortage is punctuated by these violent, temporary surpluses. That changes how the body reads. The armor is not just generic protection. It matters in close contact feeding, when multiple animals converge on the same prize, and the seafloor turns from empty plain into a jostling knot of mouths and hooks. The legs do not need sprint speed across open mud so much as steady purchase on unstable ground and decomposing flesh. The low posture, the antennae sampling ahead, the patient advance. All of it suggests an animal prepared to spend weeks in near nothing, then make almost no mistakes when the signal finally comes. Gigantism here may have less to do with dominance than accounting under extreme uncertainty. A larger body can store more after a rare feast. A slower body can spend less while waiting. But larger size also raises the stakes of every decision. If this animal misses the fall, it may face a very long blank. If it overeats or arrives damaged at the only banquet in months, recovery is not guaranteed. In a world without regular meals, timing becomes as important as hunger. The link to the surface is brutally direct. Up above, life is made with sunlight. Down here, Bathynomus lives on the failure of that life to remain afloat. Every dead fish, every torn scrap, every descending body becomes a delivery from another world. Strip away light, easy prey, and steady supply, and one answer looks like this. Not a sleek hunter, but a plated recycler tuned to both famine and frenzy. Then the plane changes. Somewhere in the dark, something heavy hits bottom. The antennae turn first. The legs quicken. Armored back flexes plate by plate as the animal crosses the mud toward the smell of opened tissue. It can wait for years, but not for this. And if one giant isopod has found the carcass already, how many more are moving in behind it? Number 4. The Bone Garden. By February 2002, the feast has already entered its quieter phase. Nearly 2,893 meters down in Monterey Canyon, a dead gray whale lies reduced to a pale framework on the sea floor. From that framework rises a field of red plumes, thin as flowers and stranger than any scavenger that should be here. An MBARI robot submarine drifts over the ribs and vertebrae. Its cameras do not find an ending. They find a bloom. Worms are making the skeleton bloom. A whale fall begins with meat, oil, and a rush of scavengers. It does not end when the flesh is stripped away. Here the scene becomes harder to recognize. You are looking at bone, not blubber. Hard calcium, a structure built to last through a giant animal's life. Yet those worms are living all across it. The question comes fast. How are worms with no mouths eating a whale? MBARI's carcass study was supposed to document a known deep-sea process. Instead, it opened a door. In 2004, Greg W. Rouse, Jill R. Goffretti, and Robert C. Vryenhoek formally described a new genus from that Monterey Canyon whale, Osedax. 2 new species from one dead whale on one patch of deep seafloor. The anatomy was the shock. No mouth, no gut, no normal way in. The females lived anchored in the bone. Their red plumes extended into the water above. Below the surface, branching tissues reached into the skeleton, while symbiotic bacteria helped release nutrients from the bone. Tiny dwarf males, almost absurdly small beside them, lived inside the female's tube. The whole animal looked less like a familiar worm than a deep-sea workaround assembled from parts that should not solve this problem. Discovery changes the scale of what a carcass means on the seafloor. A whale fall is not just a corpse lying in the dark. It is a timed habitat. For months, then years, sometimes decades, a single body can feed one community after another. Scavengers tearing at flesh, enrichment opportunists crowding the sediment, then specialists arriving for the mineral-rich remains. The skeleton is not the aftermath. It is a later chapter in the same event. One large whale can turn empty bottom into a temporary world. NOAA reported another whale fall near Davidson Seamount in 2019 at 10,623 feet. The Monterey find mattered because it showed that the final stage was not silent. After the big scavengers leave and the obvious feeding is done, the bones keep broadcasting opportunity. Somewhere in the deep, an enormous vertebrate dies, sinks, settles, and for years the seafloor reorganizes around what is left. Osedax sits deep in that sequence because it solves a brutal problem. Down here, food is rare, hard to find, and usually temporary. A whale skeleton offers concentrated carbon and lipids sealed inside one of the toughest materials in the body. Most animals cannot tap that reserve. These worms can. Their symbiosis turns bone into fuel. And because the genus spread beyond one specimen and one canyon, the story got broader still. Researchers later found Osedax across multiple oceans, and experiments showed the worms could colonize other vertebrate bones, including cow bones lowered to the seafloor. The reach of whale falls is not only about whales. It is about any durable bone that arrives in the dark long enough to be colonized. The image still resists first impressions. Above, those plumes look delicate, decorative, almost passive. At this depth, delicacy misleads. The visible part is only the signal. The real animal works below, inside the bone itself, in a place cameras barely show. The whale's body has already failed. Its flesh is gone. Its shape is gone. Yet the skeleton is still being entered. That is the answer to the riddle first seen on that gray whale in 2002. These worms do not bite bone. They have nothing to bite with. They live by partnership. Symbiotic bacteria help them unlock nutrients from the bone, while the female's branching root-like tissue penetrates the skeleton and spreads through it. What looked like a bed of red flowers on dead ribs was activity below the surface. And yet the deeper question is no longer only how they feed. If Osedax can use more than whalebone, what other vertebrate remains can it reach before the cold seafloor breaks them down? Number 3. The sunless forest. In 1977, scientists exploring the Galapagos Rift descended into a place no sunlight had ever touched and found a living field growing out of poison. Around the hot springs on the seafloor, giant tube worms stood packed so tightly they looked less like animals than a buried crop. The vent fluid around them could reach 400 degrees Celsius, yet the colony was alive. That should have been impossible. It wasn't. What exactly was feeding this forest in complete darkness? The answer was hiding in the body of the worm itself. Riftia pachyptilla does not have a mouth as an adult. It does not have a digestive tract either. It lives inside a white tube and holds a crimson plume out into the vent flow, like a flag raised into toxic weather. That plume takes in oxygen and hydrogen sulfide at the same time. To most animals, hydrogen sulfide is a poison. To Riftia, it is the start of breakfast. Inside the worm, a special organ called the trophosome houses billions of bacteria. They do the work the animal itself no longer does. They turn vent chemicals into organic matter. The worm is not grazing on scraps from the deep sea. It is farming microbes inside its own body. Smithsonian scientists first used Riftia to understand vent symbiosis, because here was a creature standing in the dark with no obvious source of food, and yet it was growing as if the seafloor had been turned into a greenhouse. By 1977, the deep ocean was still widely imagined as a landscape fed from above, a place where everything depended on rain from the surface. But at vents near the Galapagos Rift and later along the East Pacific Rise at around 2,500 meters, life was answering a different chemistry. Sunlight, no photosynthesis, no ordinary food chain, just water heated by the earth, mixed with dissolved gases, and an animal built to use both. Then the scale gets stranger. NOAA says a giant tube worm can grow to almost 5 feet in less than 2 years. That is not the slow, starved life people expect at this depth. That is explosive growth in a place where the rules should not allow it. The red plume is not decoration. It is the interface. The worm exposes its own chemistry to the vent, and the bacteria inside convert that chemistry into fuel. The forest is not fed by drifting leftovers. It is fed from within. That works only because the habitat is temporary. If a vent stops flowing, the colony can die. The hot spring shuts down. The food supply disappears. The entire field can vanish with the geology that made it possible. But when a new vent opens elsewhere, larvae may recolonize it in about a year. So the worm's home is not a home in the usual sense. It is a moving target on a restless seafloor, appearing, collapsing, and appearing again before the darkness can win completely. The giant tube worm is proof that life can rebuild itself around a chemical source the surface never uses. A mouth is gone, a gut is gone, sunlight is gone. But the partnership remains, and the partnership is the organism. In 1977, the vent field was not a barren crack in the earth. It was a forest growing from poison, held together by bacteria working inside a worm that had stopped eating in the usual way and started doing something else entirely. Number 2. The soft ghost. In September 2005, a tethered robot slipped into the Pacific about 200 miles off the Oregon coast and kept going until the world above it no longer mattered. John Delaney and Deborah Kelly's Visions 05 expedition was working near the Juan de Fuca Ridge, around 6,600 feet down, where vent fields split the seafloor and the water stays black even at noon. Then the camera caught something pale moving through that blackness. For a moment, it looked less like an octopus than a scrap of silk learning how to fly. The cute ghost, living where an expensive mistake can mean no next meal. It had the feature everyone remembers first: two ear-like fins rising from the mantle, pulsing gently side to side. People call it a dumbo octopus for that reason. The nickname is catchy, but it misses the real point. Why would an octopus down here rely on a body plan so unlike the familiar drama of shallow water relatives? No violent jetting, no obvious ink display, no burst of muscle and vanishing act. At this depth, the standard octopus defense appears to come with a punishing bill. Pressure is extreme. The water is cold, food is scarce. In a place where prey can be widely spaced, a failed escape is not just one bad moment. It may also burn calories the animal cannot quickly replace. The animal in that 2005 footage was identified as Grimpoteuthis bathanectes, one member of a much broader deep-sea group. Dumbo octopus is not one species. It is a surface nickname for several finned octopods, especially in the genus Grimpoteuthis. Even with live video, experts are often cautious about naming more than the genus. New sighting keeps widening the picture instead of locking it down. The more cameras reach the abyss, the less settled this cute animal becomes. What the camera saw off Oregon was not a shallow water octopus pushed downward. It did not punch water backward and flee. It moved with those fins, slowly and rhythmically, while the arms spread below in a webbed umbrella. Based on observed anatomy, the design points to a different economy of survival. Jet propulsion can produce speed, but repeated bursts are energetically costly. Fins likely reduce that cost. Webbing adds control and lift. In cold water, under crushing pressure, near a seafloor where meals may be sparse and far apart, efficiency is not elegance. It is insurance against starvation. And these depths are not just a trivia point. Smithsonian summaries place many dumbo octopuses near the ocean floor at roughly 9,800 to 13,000 feet. Later records pushed the picture lower. A 2019 paper reporting the first in situ observation of a cephalopod at hadal depths included Grimpoteuthis, extending the range beyond the previously cited deepest cephalopod record of 5,145 meters. The consequence is not merely deeper. It means these animals are showing up in habitats where the margin for waste narrows further, and where we still do not fully know what is hunting them, what they are hunting, or how often they can afford to fail. That softness is deceptive. This animal solved the deep without armor, and as far as we have seen, without depending on repeated high-speed escape. The fins that make it look harmless are the mechanism. They turn the body into a low-energy vehicle. Webbed arms are not decoration hanging beneath them. Together, fins and webbing create a controlled drifting profile that lets the animal hover, rise, and maneuver while holding down the muscular cost of constant jet bursts. But the fins sharpen the real question. If this octopus is saving energy so carefully, what pressure forced that bargain? In shallower seas, an octopus can erupt into action. Muscle, speed, ink, confusion. In the abyss, some of those tools may lose value or become too expensive to use often. An ink cloud, for example, is generally thought to work best where a predator is tracking visually, and permanent darkness changes that equation. Jetting still works as motion, but spending energy like a panicked sprinter may be a bad bargain when feeding chances are thin. A body built for explosive escape also has to be fed afterward. Down here, the budget appears different, and the cost of overspending may be simple. Weakness, missed prey, and too little reserve for the next threat. Years later, in 2014, NOAA's Okeanos Explorer filmed another dumbo octopus in the Gulf of Mexico. The animal showed a body posture not previously observed in serrate octopods. That sounds small until you picture the implication. The ROV lights hold on the animal for a few seconds. The body shifts into a posture no one had documented before, and suddenly, the survival problem changes shape. Maybe that posture is routine, and we had simply never witnessed it. Maybe it is a feeding stance, a defensive adjustment, or a response to the intrusive glare of the vehicle itself. With dumbo octopuses, we are still at the stage where a few seconds of video can rewrite the manual. Uncertainty matters, because most human encounters with these animals are this brief. A remote vehicle drops from the surface, floods the dark with light, watches for a moment, then leaves. We are trying to infer a life from interruptions. The dumbo octopus sits in a strange category of deep-sea animal, famous on sight, thinly observed in practice. If you drop beside it now, there is no theatrical reveal, no ink bloom spreading through blue water, no sudden rocket into a coral crevice. Just that pale body suspended in the black, fins beating with the patience of something that cannot afford waste. The likely trade-off is clear enough from the anatomy and the habitat. Lower-cost movement may matter more here than dramatic escape. But that only opens the darker question. When the ROV lights fade and the seafloor disappears again, what is this animal actually doing with that saved energy? Hunting, hiding, courting, or preparing for a threat we still have not managed to catch on camera? Number 1. The bottom fish. What kind of fish looks too soft for its own world and yet lives where the ocean presses harder than almost anywhere any vertebrate is known to survive? In 2014, on the slope of the Mariana Trench near Guam, researchers lowered baited landers into water so deep that nobody could simply swim down and look. The descent took hours. Below 6,000 meters, the sea enters the Hadal Zone, near freezing, permanently dark, and buried under hundreds of atmospheres. Cameras and traps kept dropping through black water until they reached a place where familiar ideas of a fish start to come apart. When the gear came back up, it carried small, pale animals with broad heads, translucent skin, reduced bones, and bodies so soft they looked almost unfinished. The surprise was not a plated nightmare or some giant trench predator. It was a little fish. Mackenzie Geringer and Thomas Linley were part of the team studying them. But the strangeness did not arrive as an abstract depth range on a chart. It arrived when the landers returned, and the team realized they had not captured a one-off curiosity from the trench wall. Again and again, across separate drops, the same kind of fish was there. The cameras saw them gathering at bait in a world where vertebrates were not supposed to be comfortable. Specimens came up from between 6,898 and 7,966 meters down. And one collected at 7,966 meters became one of the deepest fish ever physically recovered. Not a distant image, not a blur in the dark. In hand, measurable, real. And in a trench where Challenger Deep still falls to about 11,000 meters, that mattered for another reason. Even here, thousands of meters above the bottom, they were already near the depth where a fish body may begin to lose the molecular fight. This is the fish that seems like it should have been crushed out of existence. Picture it. Nearly 8 kilometers down. Darkness so complete it erases direction. Water just above freezing. Pressure not 10 times surface pressure, or 50. Hundreds of times higher. Enough to wreck airspaces, deform ordinary tissues, and interfere with the chemistry proteins depend on. At that point, the danger is not just being squeezed. If pressure pushes the wrong membrane out of shape, or forces key proteins to misfold, nerves stop signaling correctly, muscles lose coordination, and a fish can become unable to feed or even hold itself together functionally. Yet a vertebrate lives here. It moves, feeds, and appears often enough that researchers did not find one impossible individual. They found a population. On November 28, 2017, that fish was formally described in Zootaxa as Pseudoliparis swirei, the Mariana snailfish. The name reaches back to Herbert Swire of HMS Challenger, the 19th century expedition that helped reveal the trench itself. The connection is striking. First came the sounding line and the map. More than a century later came the realization that in that mapped void, a real fish lives there, with a face and fins and skin thin enough to seem misplaced. That apparent delicacy is not an error. It is the solution. At these depths, heavy armor is no gift. Dense, rigid structures can become a cost. Bodies that work well near the surface are built on assumptions this world does not honor. The Mariana snailfish appears to have gone the other way. Reduced ossification, fewer hard parts, less rigid framework, and more of the chemistry needed to keep cells functioning under enormous compression. Pressure does not only squeeze an animal from the outside, it acts on proteins, membranes, and the mechanics of life itself. Survival here is not about becoming tougher in the way we usually picture toughness. It is about becoming compatible with pressure. Near the lower edge of fish life, ordinary body structure starts getting negotiated away. The Mariana snailfish is not a sailor's legend. It is a documented vertebrate from the Hadal Zone, observed in the Mariana Trench, described from specimens, and built for a place where sunlight is gone, food is sparse, and the margin for chemical failure is so thin that a little more depth may begin to unravel the machinery cells used to function at all. There is one more twist in the depth numbers. This fish lives astonishingly deep, but not all the way down. Challenger Deep extends roughly 3,000 meters farther. Below the snailfish lies more trench, more darkness, more pressure, and, as far as confirmed fish are concerned, a frontier where membranes may become too unstable, proteins too difficult to protect, and the adaptations that keep a vertebrate running may no longer pay their cost. The limit is not about courage. It is about whether a fish can still remain chemically coherent. People often imagine the deepest creature as something monstrous, reinforced, armored against the abyss. The Mariana snailfish offers a quieter truth. Here, looking soft is not evidence of failure. It is evidence that the animal has been chemically and physically rebuilt for a world where our version of sturdiness stops working. And below the depth where this one still swims, the trench keeps going. If a baited lander drops farther into that black water and comes back empty of fish again, the absence may not mean nothing is there. It may mean the next few hundred meters are where vertebrate life stops being able to keep its proteins folded, its membranes stable, its muscles answering, and where the dark below is not just deeper, but newly closed.